In this lecture, we are going to derive the general conduction equation. In the first lectures, we have seen the different modes of heat transfers and the properties like thermal conductivity and thermal diffusivity. Now, we'll try to derive a generalized equation for the process of conduction, which can be used for finding out the solution of different types of conduction problems in the subsequent lectures. This we are going to do in three different coordinate systems: Cartesian coordinate systems, cylindrical coordinate system, and spherical coordinate system. So let us start. I'm going to start with some introductory notes. Then we'll derive the general conduction equation in the Cartesian coordinate system. We'll reduce this equation to different types of reduced forms, simplified form I can say, with certain conditions. Then we'll see the equation for cylindrical coordinate and spherical coordinate with their possible reductions. So this is the agenda for this lecture. I am Nitin L. Birud. General conduction equation, as I already told you, that is going to be useful for us for finding out the solution of different conduction problems. In this generalized conduction equation, the methodology, while deriving this, we are going to adopt a simple methodology which is based on the first law of thermodynamics. The energy balance obtained by using the first law of thermodynamics, we are going to apply this energy balance to a small differential element in each coordinate system, of course, and then we are going to write down the appropriate equation as required in the energy balance, and then we are going to substitute those equations into the energy balance equation to get the final form of the equation. We are going to derive this expression completely for Cartesian coordinate system, but we are going to see only the final equations for cylindrical and spherical coordinate systems. Okay, and then I'll tell you how the things are getting reduced. So let us start. A major objective in conduction analysis is to determine the temperature field in the medium resulting from condition imposed on its boundary. So when we are doing any conduction analysis, we are interested in finding out the temperature field, that is temperature equation. In other words, I can say that expression of temperature in terms of some space coordinate or in terms of some time coordinate. If you are getting this equation in terms of space coordinates, then we can simply differentiate this equation to get the temperature gradient for that particular coordinate, and this temperature gradient can be used along with the Fourier's law of conduction to find out the rate of heat transfer in that particular direction. It means that once you obtain the temperature field equation or temperature distribution equation, it will be easier for us to find out the heat transfer in that particular area, in that particular direction, in that particular coordinate system. So for this we are going to derive this generalized conduction equation. This difference, we are going to define a differential control volume, identify the relevant in energy transfer process. As I told you, we are going to apply the energy balance, simple, and introduce the appropriate rate equations. This we are going to do. Appropriate equations we are going to write for different forms of this energy equation, and then we are going to substitute it back to the energy equation to get the final form of the equation. Now this equation, whatever differential equation we are going to get, is can be solved using the boundary conditions. So in the next lectures, I am going to talk about the solution using the boundary condition, how we are going to solve the differential equation, conduction equations using the different boundary condition. And after the solution, we will get the desired thing, that is the temperature distribution in that particular medium, which is our final aim. So let us start for Cartesian coordinate system. Consider a homogeneous medium with no bulk motion, because we are not going to consider the convection, we are going to consider only conduction. So no bulk motion. The temperature distribution is function in x, y and z direction as we are talking about Cartesian coordinate system. So the coordinate axes are x, y and z. Consider a infinitely small control volume, a very small volume whose dimensions are dx, dy, dz in the respective x, y and z directions. It is shown like this. You can see that this is x direction, this is y direction, this is z direction. The dimension of this object in x direction is dx, in the y direction it is dy, and in the z direction it is dz. So, if you want to calculate the area in x direction, so for say this qx, if I want to find out what is the area responsible for this heat to flow, so I am going to get the area in x direction is going to be the product of dy and dz. Correct. In the similar fashion, area in y direction is equal to dz into dx. Okay. So this is how we are going to consider the areas. The total volume of the element is the product of the dimensions because it is a parallelepiped, and dx into dy into dz going to give us the total volume of the element. Now we are going to consider this. Here you can see that there are two things I have shown, qx and qx plus dx, means rate of conduction at x, at distance x from the origin. Okay, let us call it as qx, and what is the change in that rate of conduction at a distance dx, and that is shown by this particular term. Okay, how this term is written we'll see in the next slide. Similarly, we can have different conduction rates in y and z direction. It means that the element is having heat conducted in and out in all the 6 directions. It means that for conduction in these 3 directions, in and out, total will get 6 equations for the conduction. And in the similar way, if this element is itself is generating some energy, if some energy is getting generated, some heat is getting generated, we need to write an equation for that heat also. Similarly, because of this conduction in all the 3 directions, in and out conductions, and the rate of heat generation, there is going to be some change in the internal energy of the object. It means that we have got 3 terms now. One is the term which is associated with the conduction in the 3 directions. Second term is related with the rate of heat generation within the object, and the third term is the change in the internal energy of this object. So for that, we'll write down the equations one by one. So let us write it down. The heat conduction rates perpendicular to each of the control volume, control surfaces at x, y, and z coordinates. Locations are indicated by terms qx, qy and qz. I have shown you the value of the arrow for qx. Similarly, we can have qy and qz. And we can use simple Fourier's law of conduction for writing down the equations for qx, qy and qz. Let us write it down. So for qx, what we will get? Minus k, okay, into dy dz, that is the area, as I already told you that in x direction the area is dy dz into temperature gradient in x direction. Now instead of d, you might have seen that del is there. This del indicates that temperature is dependent on x as well as y as well as z. So it is dependent on multiple characteristics, and that's why instead of taking complete differentiation, we are taking a partial differential term. And k here stands for the conductivity in x direction, which may not be same for y and z direction. So here, although it is written only k, you can say that this is the conductivity in x direction, and already I have discussed about the negative sign. In the similar way, we can write out the equations for y directions, that is qy. You can see the area is changed, and z direction, now the area is changed, and the temperature gradient is with respect to x direction, y direction and z direction. Okay. So this conductivity values is, this is the conductivity in x direction, this is the conductivity in y direction, this is the conductivity in z direction. Now the conduction heat rates at opposite surface at some distance, say x plus dx, y plus dy, z plus dy. This can be expressed as a expansion of Taylor series. by neglecting higher order terms. Using the Taylor series expansion and neglecting the higher order terms in that expansion, we can write down for x direction this qx plus dx is nothing but the qx already it is there plus change in the value of qx in that distance dx. So qx plus whatever change is there happening in that value of qx when it is passing through, when that function is passing through distance dx. Now what is same for y, same for z. So what is this? We can write down this, we can number these equations as 1.1a and 1.1b for x direction, and where 1.1b, that is this equation, simply states that x component of heat transfer, that is qx, at distance x plus dx, that is qx plus dx, is equal to the value of this component at x, that is qx, plus the amount by which it changes, that is del qx upon del x, with respect to x times dx in that distance dx. And similarly, we can write down the equations for qy plus dy, qz plus dz using the same logic, and we can number them as 1.1 a, b, c, d, e and f. So in this slide, we have obtained the equation for conduction in all the three directions. Now we have got 6 equations. Already I have told you that we are going to get 6 equations for the conduction processes, because we are having 6 phases of the parallelepiped, and at each phase there is conduction taking place. Next slide, we'll talk about the other two forms of the equation. Within the medium, there may be some energy source term, that is the energy is getting generated within the medium. Let us call it as q dot, where q dot is the rate of energy generation per unit volume. It means that it can be expressed in terms of watt per meter cube. So if you are having this q dot equal to watt per meter cube, if you multiply it by the volume of the element dx, dy, dz, so this is watt per meter cube multiplied by meter cube, what will get? Watt. It means that this is the rate at which the energy is getting generated within the object. We have seen the equations for conduction. Now we are seeing the equation for energy generated within the object. So we have got a second equation. Let us call it as 1.2, where q dot is the rate at which the energy is generated per unit volume, and it is expressed in terms of watt per meter cube. There may occur changes in the amount of internal thermal energy stored by the material in the control volume. Now this is the third term. Second term is energy generated. Now because of this energy generated and energy conducted, the first form we have seen the energy which is getting conducted in and out from the 6 different phases. We have written the equation for that. Then second form we have seen this energy which is generated within the object, that is what is called as 1.2. Now because of these two things, there may be change in the internal energy of the object. That is, whatever energy is there, it may increase or it may decrease. If the increase is there, it will result into increase in the temperature with respect to time. If it is getting reduced, there will be change in temperature or reduction in the temperature with respect to time. So we need to have some equation which will represent this change in the internal energy, and we know that we are calculating normally internal energy in terms of mass into specific heat into the temperature change per unit time. So in differential form, and if you write down instead of mass rho into volume, that is the density of the material into volume, we can get the equation a simple form like this, that is energy stored, okay, that is this change we are calling it as energy stored within the object, because this is the energy which is getting stored. It is rho into volume, that is dx, dy, dz. So that is mass into specific heat into change in temperature per unit time. Once again, I am requesting you to pay attention to the del term. I am not using d. D represents a complete differentiation, while del, so, this small d, that is del, represents the partial differentiation. Now here what we are taking into consideration, that temperature is the function of spatial coordinates like x, y and z, and as well as it is varying with respect to time also. So it is dependent on four different things, three spatial coordinates and one time coordinate, and that's why we are taking the partial differentiation, not the complete difference. Now we have got three equations. Let us call it as 1.3. We have got three equations. One is for six forms are equation 1.1 equation. You have written six forms that represents the total represents the conduction. 1.2 represents the energy which is generated within the object, and 1.3 represents what is the change in the storage energy because of all these things which are happening into the element. Now let us combine them. When where this rho Cp into dt by dt is the time change of the interthermal energy of the medium per unit volume. The general form of the conservation energy, I was talking about this, the general form of energy conservation, that is the first law of thermodynamics, is like this: energy coming in plus energy generated minus energy going out is equal to energy storage. Now what is this energy coming in? That is Qx, Qy and Qz, because energy is supposed to come into the element at in the x, y and z direction at faces uh, which are represented by Qx, Qy and Qz respectively. And what is energy out? Which is Qx plus dx, Qy plus dy and Qz plus dz. So we have written the equations for E in and E out separately. We have got Eg, that is equation number 1.2, and we have got EST, that is energy storage, as equation 1.3, where E in is Qx plus Qy plus Qz and E out is equal to Qx plus dx plus Qy plus dy plus Qz plus dz. Now what we are going to do, we are going to put all these values 1.2, 1.3 and 1.1 equation into this equation 1.4. So next term, substituting equation 1.2, 1.3, 1.5 and 1.6 into equation 1.4, we'll get Qx plus Qy plus Qz plus Q dx dy dz, that is the energy generated, minus x plus dx dy y plus dy minus dy z plus dz is equal to energy stored. So now we have got separate equations for Qs, Qi, Qz and Qx plus dx, Qy plus dy, Qz plus dz. Now substitute all these equations into this equation. Let us call this as equation as 1.7. Now in 1.7, we are going to substitute from equation 1.1a to 1.1f. So if you substitute the values of Qx, Qy, Qz, Qx plus dx, Qy plus dy and Qz plus dz, you will get this. That is my minus del qx upon del x into dx minus del q upon dy upon into dy plus d, like that, and in this term will remain as it is, q dx plus dy plus dz and rho cp into whatever. Let us call it as 1.8. Now qx, qy and qz, you can recall that we have got equations 1.1a, 1.1c and 1.1f, sorry, e, in which we have written the equations for Qx, Qy and Qz. So using this 1.1a, 1.1c and 1.1e into equation 1.8, and what is the common thing? Dividing out the dimensions of the control volume, that is dx, dy and dz. So substituting the values of Qx, Qy and Qz in these equations and dividing the entire term by the volume, that is dx, dy and dz, will get the final equation as this. That is del upon del x in bracket k into del t upon del x plus del upon del y k dt upon del t upon del y plus del upon del z k into del t upon del z plus q dot. Now this dx dy dz is cancelled because of it is divided, and this dx dy dz is also cancelled, and you will get this term. So now let us try to this is actually our final equation. This equation 1.19 is the general form of heat diffusion equation for the Cartesian coordinate system. So this is our final equation. Let us try to understand this equation in detail. Now what is there in this equation? You might have noticed that there are three terms which are representing the space coordinate. That is, the temperature is a function of x, temperature is a function of y, temperature is a function of z. So these first three terms are representing the temperature variation in the space coordinates, which x, y and z respectively. Second thing, you might have noticed that k is inside the bracket. It means that k is dependent on the value of x, this k is dependent on value of y, and this k is dependent on value of z. Means this is the conductivity in x direction, conductivity in y direction, and conductivity in z direction. They are not same, they are different, and that's why they are inside the brackets. This is about the spatial coordinate. This particular term q dot, as I told you, that is watt per meter cube, that is the rate of heat generation within the object. So this term represents the energy generation. So whenever in a problem rate of heat generation is specified or heat generation is specified, then we need to consider this particular term q dot into picture. And then this term del T upon del T, that time, temperature as a function of time t, small t, represents the variation in temperature with respect to time. It means that whenever temperature is varying with respect to time, we have to consider this. Now let us discuss further. We understood the concepts of these terms. Now, if the problem is of steady condition means temperature is not changing with respect to time. So under steady condition, this term del T upon del T will become 0. It means that this entire term will become 0, and this whatever left hand side is there, it will become equal to 0 under steady conditions. If there is no internal heat generation in the problem, this term q dot will also become 0. And if there is no noticeable variation in the temperature in say y and z direction, the variation in the temperature is negligibly small, then this del T upon del y and del T upon del z terms are also going to become 0. It means that we can reduce this equation to the required condition. Suppose a one dimensional problem we are considering without heat generation and without or steady conditions, with steady conditions, then the equation will reduce. This term will become 0, this term will become 0, this is 0 because heat generation is 0, it is steady, so that's why it is 0, and the equation will reduce to del upon del x into k into del t upon del x. And in that case also one more simplification is possible, that if you consider that k is a constant, k is independent of this direction, then this k can be taken out and this equation will become del square t upon del x square. Del x square is equal to 0. So this is how we can reduce the different forms. In next particular things, we are going to discuss about the different types of problem. What type of problem we are expected to solve? We are expected to solve one dimensional conduction problem without heat generation. That is this under steady condition. So this we are going to ignore and this we are going to ignore in the first problem. In the second problem, we are expected to solve one dimensional steady state conduction with heat generation under steady conditions. So this is also going to become 0 and this entire term will become equal to plus q dot is equal to 0. So in that way we can reduce the equation and we can find out the solution. Let us take a look at some forms, some typical forms. If the thermal conductivity is a constant, so we can take out that k uh, from the all the brackets, and if it is a constant means k in the x direction is equal to k in y direction is equal to k in the z direction, means if the material is isotropic, we can reduce the equation in more simplified form. Now the k is taken out from the bracket, that's why it is becoming del square t upon dx square, del square t upon del o square, del square t upon del y, del z square. K is taken out and it is taken into division. So it is divided, entire equation is divided by k. So this term will become q dot upon k. And here it was rho Cp upon k. Rho Cp upon k. We already introduced a term called as k upon rho Cp and we have termed it as thermal diffusivity. So this term will become 1 upon alpha and then this equation del T upon del T. So where k upon rho Cp is equal to alpha, and that is already you have seen it as taken as thermal diffusivity. Now this equation under steady conditions, this term will become 0, no change in the amount of energy storage, and the equation 1.9 will reduce to this form. 1.9, the previous one. If it is 1.10, then this equation under steady conditions will become, this term will become 0. So del square T, this plus Q by K is equal to a big 0. So this is how we can reduce it. Then if the heat transfer is one dimensional, that is say in x direction only, and there is no energy generation, under steady conditions, equation 1.10 reduces to, see what I am saying, one dimensional, that is only x direction, there is no energy generation, means this is also 0, and there is steady condition, means temperature variation with respect to time is also 0. So equation 1.10 will reduce to this form, del square T upon del x square is equal to 0. Or now temperature is dependent only on x, so we can simply write d square T upon dx square is equal to 0. The solution of this particular equation we are going to obtain as our first problem. So in next slides, after learning about the boundary conditions, of course, I am going to solve this particular case. Now, whatever we have done for the Cartesian coordinate system, similar kind of things can be repeated for the spherical coordinate systems and cylindrical coordinate system. I am going to give you the final forms of the equation and some reduced form just for your understanding. So let us, in cylindrical coordinate system, the coordinates are r, that is the radius of the cylinder, z, that is the height of the cylinder, and theta, which shows the angular angle, change in angle. So r, theta, z total, if you specify the values of r, theta and z, you can specify a cylinder. So in cylindrical coordinate system, the general form of heat conduction equation is like this. Once again, it's a big equation, but don't get confused. Similar things is there. Here the temperature variation is with respect to r. So this first term indicates the radial variation in the temperature. This term is representing the temperature variation in this direction phi, theta, whatever is there, and in this direction it is z direction. So this first term represents radial with some angle and with some height. Then the heat generation term and the uh, heat storage term, they are going to remain same. And if you reduce it to the one dimensional form with steady conditions without any generation and only radial heat conduction is considered, then it will be reduced to 1 upon r d upon dr, r dt upon dr is equal to 0, because this is 0 and this is also 0. This term with respect to phi and z are also 0. We have got only this particular term, and that in that case also k is taken as, k is taken outside because it is constant. So if you consider that conductivity is a constant and radial heat conduction, then we will get this particular simplified form of this equation. Similar conditions can be repeated for spherical coordinate systems, and in the spherical coordinate system, the coordinates are r, r, theta and phi, and in r, phi and theta, and for this generalized form it's like this. So first this term is representing r, this is representing phi, and this is representing theta. So if you represent r, phi and theta, this is heat generation term and this is the energy storage term. So if you reduce it to the one dimensional conduction without heat generation with constant thermal conductivity without under steady conditions, the equation will be reduced to this form. 1 upon r square d upon dr, r square dt upon dr is equal to 0. You might have noticed that in the cylindrical coordinate system, we have got the same equation, only instead of r square it was r. So that is the difference in the one dimensional form of steady conduction equation in spherical and cylindrical coordinate system. So in this particular lecture, we have learned about the general conduction equation, we have derived the expression, and we have studied different forms. We have studied the different forms of equation for cylindrical and the spherical coordinate system. Next time, we will be discussing about the boundary conditions in order to solve this particular problem. Thank you. Thank you.